I guess some of you have trains, and as we were discussing with the organizers, I'm even a bit surprised that there are still so many people around. I would have thought, so I won't take it personally if you sneak out because you have a train. I mean, that's definitely in my mindset that those kind of things can happen. So maybe just during the break, someone told me that I made a mistake in the value of B. So I mean, that's the actual value of B. But somehow the final formula was correct, and that's the one which I had in mind. So this last formula is still the correct one. The B was incorrect. So now the question is, I mean, when we do this reconstruction error, what are the optimal choices for E and D? And that's where you have, I would say, a result that's not fully obvious, which is the following. So there is a lemma which says that when you do this infimum of Rn hat over E and D, or in fact over E, D, and B, so even the first one here, so E being a matrix in D times L, was that, yeah, wait, I had. D is a matrix in L times D, and B is a vector, is a line vector in 1 times D. Then this thing is equal to it's a minimum, meaning that the infimum is attained, and you can reduce it to a minimum on a single matrix V, which is of dimension L times D, and which is such that V transpose is equal to identity, meaning that V here, it's a basis of orthonormal vectors. I mean, that's what it means, because in this, if you think of V as being a matrix at L times D, it means that you have like a V1, V2 until some VL. And so this condition then reads that it's a V transpose. So the entries here are Vi scalar product with Vj. And so you want this to be delta ij. So you want this basis, those basis vectors V1 to VL to be orthonormal. So that's what it means in this fancy kind of matrix language. And so the of xi minus xn bar. So I had also an interesting question at the break on whether x is centered, and that will be the case if I do something like standardization. Then naturally all columns will be centered. But if I do something like a min-max scalar, maybe I'm not centered around 0. So maybe I need to to consider this bias xn bar up, and so minus xi minus xn bar, and then V transpose V. Voilà. So it's in the end, it's there is only one V matrix that appears, and so my encoder, I'm encoding with V transpose, and then I'm decoding with V. So it's the same that's being used for encoding and decoding. We'll see that when we do the nonlinear generalization with autoencoders, I mean, some people will insist on having symmetric architectures for the autoencoder and maybe even tied weights, meaning that the weights for the decoder are the transpose of the weights for the encoder, and the origin would be that. But somehow you can have more flexibility than that for neural networks. So, okay, so that's the result here.
This means that ED at the minimum can be written as BT times D.
Yes. So here I'm really minimizing over all possible matrices. But in the end, I can reduce this minimization to E and D being tied by this relationship, and also the matrix that appears here is obtained by from some orthonormal family. So particularly, it's not like a 0 matrix. I mean, it's because here E and D could be 0, but of course, if they're 0, then you make a large reconstruction error. You want to see the proof or not? No, okay. So you can read the proof. No, I mean, it was a genuine question because I don't insist on writing the proof, and maybe it's counterproductive at this time of the day. It's not that complicated, though, if you take it fresh in the morning, but it's in the lecture notes. Maybe the more interesting thing is to go to the 1D case. So to the case L equal 1, and look at what's happening then. In this situation, in fact, your V matrix is simply a vector. So the minimization error, in fact, you can, okay, let's replace xi by xi minus xn bar. So let's assume that I've recentered my data. And then I'm looking at quantities like xi minus xi v transpose v squared. And so this, in fact, is xi squared minus xi vt transpose v squared. So you expand the square and I mean, that's what you obtain by an orthogonal projection. So the fact that I mean, this thing here should be seen as the sum of xi scalar product with vk multiplied by vk. So for k equal 1 to L. So this is something in the range of the matrix V, so spanned by the vectors from V1 to VL. And so this is something that is orthogonal to all, to V1 to VL. So those two vectors here are orthogonal, and that's why Pythagoras' theorem tells you that you have this equality. And so the reason why I'm rewriting it like that, so maybe I can also even do like a plot. You would have a vector xi. You would here have the range of V. Here you would have xi v transpose V. So the orthogonal projection onto the space spanned by V1 to VL. And then the reconstruction error, it's that thing here. Reconstruction error. And so minimizing the reconstruction error somehow is maximizing the norm of the projection. That's I mean, just to say that. So it's maybe easier to look things up that way. So that I want to maximize for the sum from 1 over n of xi v transpose v. So maximize over v for v's which are such that v transpose is the identity in L. So that's what I want to do. And so in the 1D case, this amounts to maximizing over vectors which are of norm 1. Because in 1D, then, this, when L is equal to 1, this is just saying that my matrix V, I mean, this is just a row matrix, and the norm of the vector that appears in the row is 1. And then here you have, sorry, I'm missing a sum from I equal 1 to n. Here I have a sum from I equal 1 to n of xi scalar product with V. So here I've just been rewriting that quantity when I have when I'm in dimension L equal 1. And that thing here is, in fact, it's simply xi scalar product with V squared, because the norm of V is 1. Okay, so overall, what appears here in there will be V, the sum of xi transpose xi, V, for I equal 1 to n, V transpose. So here I'm working with line vectors, so that's why this is really a matrix, this is a column vector, and this is a line vector. And so this quantity is maximized when V is an eigenvector associated with the largest eigenvalue of that matrix. Is that clear to everyone? I mean, if you don't see it, I mean, this matrix is symmetric, you diagonalize it, and then, you put all your mass on the diagonal element, which has the largest value. So this means that this is maximized for V unit eigenvector associated with the largest eigenvalue of the covariance of the data, which is sigma hat equal 1 over n, the sum of xi minus xn bar transpose xi minus xn bar. And somehow that's the usual PCA conclusion. And PCA tells you that, okay, construct the covariance matrix of the data and take the largest eigenvectors of that matrix. And here you see that we really obtain the same result from this perspective of reconstruction error. And the perspective of reconstruction error, and maybe that's a good moment to come back to the initial motivation. I mean, it's really something that is natural for supervised learning. So here in supervised learning, we're only being handled data points. We don't have any labels, and we have to find patterns in data, some structure in the data. And here the idea is that does the data concentrate on a lower dimensional manifold? And if you have that's a linear method for trying to identify such a submanifold, which would be an affine space, if indeed there is an affine space which concentrates most of the data. So that's the case L equal 1, and for L larger than 1, in fact, you find that, did I have anything else to say? No, that's not. You find that UV is equal to U, which would be something like U1 to UL, which would be the unit, an orthonormal family of vectors Ui associated with the largest eigenvalues. UK associated with the L largest eigenvalues of sigma hat. So here as well, there is a proof of this in the lecture notes. It's essentially a generalization of the proof in the 1D case. The proof in the 1D case I like because it's really like a one-liner. In the I mean, if you have L more than 1, in spirit, it's not more complicated than over there, but it's computationally heavy. And for the sake of keeping you alive until the end, I'll spare you the details of that. But it's really, I mean, there's really nothing too deep conceptual. Maybe a good time to discuss the choice of L. Because in all this, I mean, unsupervised learning, well, no one's really telling you what to do. I mean, supervised learning, it's clear, you have labels, you want to predict them. Unsupervised learning, it's more like, hey, here is some data, try to figure out something with it. And here in particular, one question with PCA is, what is the intrinsic dimension of the system? How many components do we need to describe it with a good accuracy? And so a typical thing that people would do, you would report the reconstruction error as a function of the dimension L. So that's, of course, usually with PCA, people would with more talk about, well, maybe I'll do it the in PCA, people would rather report an eigenvalue lambda k as a function of k. So you'd first have a largest eigenvalue of the covariance matrix, then a second one, a third one, and so on and so forth. And typically you have things like that, which are called the scree plots, where you report the eigenvalues as a function of the index, and you're looking for something like an elbow or some some change in curvature here in the curve. So you have like eigenvalues which are rather good, and at some point there is something that decreases less, let's put it that way. Or if you look at the cumulated sum, lambda 1 plus lambda k, which is the reconstruction error. Because in fact, one thing I have not said is that when you look at the reconstruction error, in fact, it's no, it's like it's not the it's not the reconstruction error. It's how much you the reconstructed fraction, something like that. So how much of the data you do reconstruct. So that thing here, so it's really that part as a function of L. And you could maybe, normalize a thing so that you really have a fraction. So to divide by the norm of xi squared, so and to have a number between 0 and 1, which tells you which percentage of the variance you've obtained or which percentage of the reconstruction is fine. So initially, it will start off with large values, and then at some point, it will stall a bit. And so the general practice is to say, okay, look for a point on that curve where the marginal increase starts to be smaller. So like an inflection point on the curve. That's what is meant by this knee in the scree plot. Yeah. Which I'm not familiar with. So I cannot answer the question. So one point here is that the more dimensions you add, the better the smaller the reconstruction error is, and the larger the reconstructed fraction is. So I mean, if there is nothing like a validation procedure here, because the validation procedure, if we're trying to maximize, to minimize some reconstruction error, the answer would always be take all dimensions. So that's why we're coming up for some criterion which is more like hand wavy than what we actually have for supervised learning, where we have a validation error to make the choice of parameters and so on more objective. So here it's more subjective, like how many dimensions will we keep in the end? And that's a problem I'm facing on a daily basis when I'm working on molecular systems. And our answer to that is that in the end, we want to retain 2 or 3 degrees of freedom, because we want to do some free energy computation, and we cannot do it in more than dimension 2 or 3. So sometimes, you have like external guidelines for saying that let's keep so many degrees of freedom. But otherwise, maybe sometimes you don't know, and well, you have to come up with ways of choosing them. Alors, PCA, did I want to say something else about PCA? No, maybe not. I mean, the other things, I mean, there are lots of other things to say about PCA, but somehow it's a bit too, it's more for data mining or interpreting the results and so on. So there's not, in particular, something about when you take the PCA, the first 2 PCA vectors, apply them to the data, it falls into a unit ball, and then there are ways of leveraging that interpretation to understand what PCA is doing, grouping the points, understanding what you're retaining in the data. But I mean, I'd say that's a bit too statistical a way of looking at things. So if you do data science, it's important that you know more about PCA than what I just said. If your aim is to find the reaction coordinates in molecular systems, maybe let's stop here and let's go to autoencoders. And so which is the nonlinear generalization of PCA. Voilà. Alors, autoencoders, I mean, somehow it's already, we already have more or less everything we need to understand them. And so it's a neural network which takes as an input the data point xi, so something which has a dimension d, so x, which is a vector in dimension d. Then you have a certain number of layers, which, something that can be arbitrary. Maybe you start by increasing the dimension, then you decrease, and so on. You have many layers, and then in the middle, you go to a bottleneck, which is of size L. And after that, you do other things until you go back to an output which is of size D. So the same dimension as the input. So if somehow in the middle, you never have a layer of dimension less than D, then your autoencoder is simply copying the input to the output. I mean, that's the easiest case situation. If the network is too large, somehow you're just passing the information from the beginning to the end and copy, and then the reconstruction error is 0. Here, this cannot happen because in the middle, there is a constriction in the information. You have to compress the information to something of dimension L, which is strictly smaller than D. So you are making some reconstruction error. So the first part here of the encode, it's an encoder, and so there are parameters θ1 associated with it. So the weights and the biases until you arrive at the activation functions here in the bottleneck. And then there is a decoding function, which is sorry, it's θ messed up parameters, of course. And then a decoding function for which you have parameters to go from the bottleneck to the output. And here, somehow I'm composing it that way, but it's really an autoencoder function which has a certain parameter θ. But I like to see it as the composition of an encoder and a decoder. Also because in practice, at least in my molecular dynamics applications, it's mostly the encoder I will care about. But to get the encoder, I need also to train a decoder. To me, it's the end of the encoder. So I mean, this f-onc function, it's going from RD to RL. And the decoder, it's something that goes from RL to RD. Does that answer the question? Yeah. Symmetry between encoder and decoder? There need not, but I mean, in practice, fair point. I mean, in practice, in particular in the early ones, so those autoencoders, I think it's about 1986, and they were called auto-associative networks. So they were meant initially as a nonlinear generalization of PCA, and for that reason, somehow from going for the first layer to the second layer, the weights and biases were transposed here. So I mean, so the architecture was completely symmetric, and also the weights used in the encoder are also used in the decoder, but in a transposed manner. So those are the old-fashioned autoencoders, let's say. It's like going to another space. Yeah, I mean, just that here you want something that reduces the dimension, then extends it. And if you believe in the proof I've made in the PCA case with these ED matrices, the proof I did not write in the PCA case about those ED matrices, somehow you should more or less the outcome of the minimization of the reconstruction error will automatically come out with neural networks that will do this kind of dual job, but maybe not directly with dual weights. I mean, it's a function that will be the dual, but maybe it has different weights. It just has the same action on the data points. No, and maybe it doesn't, but I mean, in some situations, some people have been playing around with asymmetric networks. We have been doing as well. I mean, probably won't be telling that, but the decoder essentially can be understood when it's really large as some form of conditional expectation. And so maybe, I mean, I would say that if you have an encoder that's small, maybe your decoder should be extremely expressive so that all the error comes from the encoding and not from the decoding. That's my take on autoencoders, is that it's really this compression part where you're losing information, and so maybe you should do something asymmetric, not to make extra errors, unnecessary errors on the reconstruction. But it's a bit of a personal viewpoint at the moment, I'd say. So let's keep it open, make it symmetric or not, that's your choice. But in the end, I mean, so it's really this thing that we want to minimize over theta. So over all our parameters theta. And maybe I'm not explicitly, so maybe I can add some regularization, maybe not. So here you could say that maybe I take a neural network with a lot of layers and very wide and so on, and maybe it's too expressive, and maybe I want to put in some regularization. But because you're minimizing reconstruction errors, the risk of overfitting is not that large. And anyway, after that, when you train them, you use early stopping, and early stopping in itself is already a regularization procedure because it prevents the training loss. It prevents you from overfitting because you're monitoring the validation loss. So somehow in practice, it's not really useful. My experience is that it's not that useful to introduce some regularization. So dropout, whatever, not really so useful. Voilà. What do I want to say about? Because otherwise, I mean, I have some messages which are a bit technical about those conditional expectations and so on, but maybe I don't want to. I don't want to tell them. So maybe I'm just saying what we do with them in free energy computation, and then if I have time, I'll discuss a bit clustering. So in MD, f_onc can be used as a collective variable for free energy computation. So how many of you are familiar with the free energy collective variables and so on? Some. Also free energy computation. So I'd say that those of you who already are familiar will understand from a few lines, and for the others, I mean, just a teaser for knowing a bit more. So when I have a molecular system, Q in some space, let's say molecular system where I have positions Q equal Q1, Qn for my atoms, and I have associated momenta P1, Pn. So the moment. And typically I'm thinking of, say, some protein, some complex protein, up. Voilà, so like, yeah. let's make it to butane. Some complex protein in some solvent, water, and so I would like to understand the macroscopic state of a system like that. And if you see in butane, I mean, typically it's characterized by two angles here, two dihedral angles that dictate the most relevant features of the molecule. So I can put a lot of solvent molecules, one butane, and in the end, it's really those two angles that mostly characterize the conformation. So that's the notion of a collective variable. It's a function psi, which goes for my full configuration state space. So I'm putting that in a space D. So D here would be typically a simulation cell with a periodic boundary condition. So a cubic box of size L, periodic boundary conditions. So this would be my space, a high dimensional space. And this would go to something of a much smaller dimension. So something like R to the L with L much smaller than 3n, typically 2 or 3. But typically or ideally something of order 2 and 3. So collective variable. And so what do we do with a collective variable like that? I mean, it's supposed to summarize a bit the macroscopic state of the system. And this is something you can understand in terms of a free energy. So I'm assuming that everyone had a little bit of thermodynamics in his or her life. I mean, I guess that it's difficult to do physics or chemistry and avoid thermodynamics at all. Although I have to be honest, I started understanding, or maybe understanding is a bit too preposterous. I started feeling more confident about thermodynamics the way I did statistical physics. And in particular, the concept of free energy. I mean, it's the thing that tells you that exponential minus beta f of z. It's the, so you consider the Boltzmann-Gibbs probability measure, normalized, and you look for all the values of xi which are equal to some target value of z. So z here you can think of, let's fix the value of those two dihedral angles for butane, and let's look at all the possible molecular conformations under the Boltzmann-Gibbs measure where I have exactly those two values of the angle. So I can play around with the solvent, the bond length, the bond angles, whatever degree of freedom I have in my system, but I want those two things to be fixed. And so mathematically speaking, it's this delta measure, which, if you're a big fan of the co-area formula and so on, and for the mathematicians in the room, this is a normalized Lebesgue measure. So it's the Lebesgue measure induced on the submanifold. You don't need to understand that sentence, but for those of you who like math, here I'm working on all the molecular configurations for which psi of q is exactly z. So that's a submanifold. And I'm undoing this submanifold with a measure which is the normal, which is the Lebesgue, the induced Lebesgue measure divided by the norm of gradient psi. That's what's behind the delta measure. It's yeah, that's but here it's more like marginal. Conditional would be if you renormalized by exponential minus beta f. But anyway, so I mean, so that's the definition of the free energy. And the only thing I want to say here is that typically you would plot a free energy profile of a free energy landscape. And on the free energy landscape, you would identify local minima, and those would correspond to the important configurations. And maybe you care about pathways for going from one conformation to the other. And so when you have a plots like that, what are the important free energy minima and what are the pathways from going from one to the other, you already learned a lot about your molecular system, and you can start to think about computing rates to go from one product to the other, reaction rates and so on. But I mean, the free energy is really something useful for interpretation, and also in molecular simulation, it's useful to run the dynamics. I mean, if you run just Hamiltonian dynamics on a system, on a typical system, it will be metastable, meaning that for butane, it will remain stuck in some conformation for a rather long time before switching to another. And maybe you want to speed up that process. And you can speed up that process by running simulations with a potential energy function V, which is replaced by V minus the free energy. And then you really or maybe you add a little bit of parameter here. That's what's behind the adaptive Bayesian free energy methods, metadynamics, and so on. All those kind of techniques that really make the system explore more easily the configuration space. If I've lost you, the important thing here is this choice, the choice of the collective variable. I mean, the point is to find something that is relevant to the system and that allows you to, that allows to identify the correct degrees of freedom to bias or to understand. I had a question somewhere? No, bad question. So how do you choose a good collective variable? Well, there were the good old times, 10, 20 years ago, where chemical and physical intuitions were prime things to do that. So you would live with your system, cherish it as you go. You'd be the world specialist of it, and know how to choose what are really the relevant degrees of freedom that dominate the transition and the evolution of the system. And you'd obtain that knowledge by watching movies of MD simulation for hours, because Netflix was not a thing at the time. So that's what you were doing in the evening. Nowadays, machine learning has a promise of doing that job for you, automating it, and going beyond or at least complementing human intuition. And so that's where autoencoders come in handy as one of the methods. But I mean, the method I prefer, I mean, that's why I'm presenting them. That's the method I currently prefer, at least to identify those collective variables and really as the encoder in this reconstruction era. So to me, I mean, really the key degrees of freedom of the system, the values of reaction coordinate is what you have here in the middle in the bottleneck. So one thing is that if I want to use this in molecular simulation, I will need at every step, in particular when you do those kind of free energy biasing, you know that you will need the gradient of your energy. So you will need also f prime of psi, gradient of psi. So you will need to compute the gradient of psi in your simulation, more or less at every time step. And that's an incentive for here making the encoder maybe a bit not too complex, so that you don't lose so much time when you need to call like Plumbed or PyTorch, whatever, compute the gradient and then bring it back to you. Especially because this gradient of psi, I mean, will be done by automatic differentiation. So that slows down things, and so there's an incentive keeping it a bit on the smaller size. And on the other hand, training the encoder and the decoder, that's typically something that you do offline, not at every step of the simulation. So that's why I'm saying that you can be more generous about the decoder, maybe take it larger. So the typical way it would be done, I mean, I'd say that there are two options. Either you're fully unsupervised, and sometimes you're fully unsupervised in life, like you're being handed a new physical system and you don't know whether there are how many metastable phases there are. And sometimes you're a bit more you're semi-supervised, meaning that you know that if you have a protein, that there are different conformations in the protein data bank, and maybe you run a little bit of a simulation in each conformation, and then you have information that comes in with a little bit of labels. So let's discuss a bit the two situations. So first, in the fully unsupervised case, typically what I would say is that you do some iterative procedure, which is nowadays rather common for people doing ML in molecular dynamics. So you would start from you do some sampling / exploration. Typically something like Langevin dynamics with a free energy biasing. Based on current CV, collective variable. So initially at the first step, you have nothing, so you just run a bare Langevin dynamics, so Hamiltonian plus some noise. You do some exploration, and then you have a few conformations, a few configurations. And once you have a few configurations, you train an autoencoder to update Xi. And then you loop. So typically you start take something from a protein data bank, you prepare your system, solvate it, and so on. You run a bit of a trajectory, you record a certain number of configurations, with some period, not every step, but every picosecond, something like that. And you have a first data set, and then you train an autoencoder on that. And this will give you a first encoder. So that's your first guess for the reaction coordinate. Then you do some free energy bias simulation. So you're replacing the potential of you're biasing by some fraction of the free energy in an attempt to explore a bit more freely, to navigate more the configuration landscape. So then you explore a bit more, you have new configurations, and then you use them to update the reaction coordinate. So maybe you need to put some weights to compensate for the importance sampling here. And maybe you also retain some history, keeping some past configurations at the previous step and so on. So there is a whole, I'm remaining, so I'd say, I'm remaining a bit vague on how this is done in practice because it would take us to regions which it would be too technical somehow. But then you really iterate between the two, between some exploration phase and some exploitation phase where you update the reaction coordinate until you reach some convergence criterion. For instance, the reaction coordinate hasn't changed much, or probably better, up to some affine transform, something like that. And here, of course, I'm hiding a few things under the rug, in particular, the fact that which features do you feed your autoencoder with? And so you can work in internal coordinates and maybe only the internal coordinates of the part of that is of interest to you. So you get rid of the solvent degrees of freedom, and maybe you take only the carbon backbone if it's an organic molecule, or maybe only the C alpha carbons if you work with a protein. So that's one thing. And if you work with like atomic positions, then probably you need to realign with some reference configuration so that the molecules always appear in the same fashion. That, or you do something like Geneviève mentioned about data augmentation, that you put in an atomic configuration and various other translation and rotations of it. So there is quite an engineering side on that. But essentially the idea is there. Explore, update, reaction coordinate, and then explore more. And then there is the semi or supervised case where you would have short simulations from various metastable regions, metastable configurations. And so here, typically, I mean, from the short simulations would be too short to see a transition from one state to the other. So you would remain stuck in some local minima, but at least then you have a database where you have configurations for all those metastable configurations. And then you can do your autoencoder, retain a certain number of degrees of freedom, and then you can look in the latent space somehow, or how ideally you would want a reaction coordinate that does a job like that, something that you would have a metastable state 1 here, state 2 here, state 3, state 4, and ideally they would be separated one from the other in latent space. And so then the hope would be that there would be a path in latent space that allows you to do a transition from one state to the other, and then you can really navigate this kind of lower dimensional landscape to find those transition. And once you have a transition latent space, you can decode it to an actual transition in atomic space. So that's the other hope in terms of, I mean, more like the semi-supervised case. And here we would know that we have labels from being in one of the states or the other. Yep.
I had about collective variable that was feeling like the important thing is not really to decode rather than to have a good representation of the energy density somehow. So
it's really the encoding part that's important. But here to learn a good encoder, you need to have a good decoder. I mean, you learn them jointly, but I really see the decoder as being some function which is there to find the right encoder. So somehow in this process of minimizing over the encoder, I would really I tend to think of it as minimizing over the decoder first. Fdec rond f enc of x. And after that only, and so let's put an expectation, say that, I mean, like summed up over the data points or something that is really like an expectation over this unknown probability distribution. So I really tend to think of it that way, as first minimizing over the decoder, and the ideal decoder, in fact, you can show that at least in this rewriting, that Fdec of Z is the conditional expectation of X, given that F enc of X is equal to Z. So it's simply somehow the average configuration that you get for all the configurations for which the value of the encoder is fixed. So that's why I'm thinking really of as the encoder as being the prime thing, and from there the decoder just follows.
Optimization step, we feel like what's important is like properly describing the representation. So I don't know, intuitively would have been
like you would want to, I mean, that's your point. I mean, some people there are various criteria for choosing a correct reaction coordinate, some of them being that the free energy barrier should be maximized, which mathematically turns into the fact that there is some functional inequality, a Poincaré inequality that should have a maximal or minimal constant. So it, I mean, there are ways of quantifying what you say, but here indeed it's not related directly to that, because what I said about Poincaré inequality, for instance, uses some gradient or some effective overdamp Langevin dynamics, and here it's a fully static viewpoint here. I mean, yeah, there is no notion of evolution of time, no dynamics, no nothing. Which, I mean, for free energy, there is nothing either, but yeah, no, it's not directly, it's more like really this reconstruction perspective that tells me that if data is really gathered on some lower dimension manifold, I hope to identify it by that procedure. There are extension, but now that I think of it, there are extension to the time evolution. So here we have been discussing data as new points that are being independent and drawn from the same probability distribution. There are versions of autoencoder which are called time-lagged autoencoder, where you have to predict to do a minimal reconstruction error on the next configuration from the previous one. So that's something that is also supposed to learn. That's an encoding that's relevant to the time evolution. But yeah, there are some. I'm not discussing there because there are some limitations, some caveats. It's more. But I'm still mentioning the existence. I had a question over there. Okay, I didn't get the beginning of the question. Yep. Are we slow? No, here we don't know anything about slow. I mean, so here it's really a high variance perspective. So the typical counterexample to that would be a situation like this, where you would have here a high free energy barrier to go from one of those states to the other. So the high variance direction is this one. The slow direction is this one. So here high variance, and here it's slow. So I mean, in principle, this has nothing to do with dynamics, and so you don't know about the slow degrees of freedom. What I've seen in practice is that, surprisingly enough, or not, what you get from here still has some dynamical relevance. One of the things we have done in some work, which I mean, it's a bit too technical for that, is to see that the path that you get from the ideal decoder here converges to some minimal energy path in the small temperature limit. And so this indicates that there is some kind of a dynamical relevance to the autoencoder kind of framework, but it's still, a bit, it's a motivation more than a proof by itself. Questions on that? So if not, maybe I'll take the last half an hour to briefly discuss clustering, which is also, now that I've done my job to relate the past 8 hours to molecular dynamics, I'll feel confident in doing something that is not directly related to it. Although clustering, I mean, my experience is that you need it at some point when you do science. In particular, when we do molecular simulations, at some point we don't know, especially free energy bias, we observe new configurations and we're not so sure whether it's configurations we've already identified or new ones. And clustering, I mean, there is a promise there that maybe you have automatic ways of detecting whether, I mean, how many groups you have, how many classes, and whether they are new ones. So that's another method which is unsupervised, meaning that you only have data points xi, and you don't have labels. And the typical question in clustering would be, how many classes you want to make groups. So I mean, the idea is that elements, I would say, similar elements in the same class, and elements which are dissimilar in different classes. It sounds like I'm saying twice the same thing, but not quite. Dissimilar elements in different classes. And there are two difficulties, I'd say various major difficulties with clustering. First one is the lack of ground truth. So I mean, it's really difficult to work, to come up with new methods for clustering and so on, and to say that one is better than the others. Typically because you're never so sure about what's the best partitioning. So of course there are some synthetic data sets where you have labels and you test the clustering algorithms on the data without the labels. So for instance, if I give you pictures of FCC and BCC metals and images. I'm not saying how you obtain the images. You probably know better than I do. And I want a clustering algorithm to classify the BCC on one side, the FCCs on the other, without giving the labels. That's something you can check a posteriori by looking at the pictures and then having some expert identify BCC and FCC and looking at the percentage of accurate predictions. But most of the time you don't have a good ground truth, and so you don't really know, you don't really have a good metric of how well you're performing. Whereas in even like dimensionality reduction, you have some metric which is the reconstruction error. Here it's finding a metric is somehow part of the question. That's one thing. And in fact, the very definition of clustering, it's also difficult. I mean, it's somehow similarity is not a transitive relation. It's not transitive relationship. And what I mean by this is that if I'm let me draw two group of points. Something like that, something like elongated like that. And if you say that this point is close to that one, which is close to that one, which is close to that one, and so on. And so we're grouping them together. In the end, if you end up grouping together all those persons, and maybe the first one is extremely different from the last one. They're still in the same group. And so maybe it would make more sense to group this one with that one because it's closer. But that's where different, there are different ways of different metrics in the clustering algorithm and so on. And some clustering algorithm will separate the data in those two clusters. Those others will separate in those two clusters. And maybe the two answers are correct. It's more what are you expecting? What are you actually expecting when you do clustering? And that's when I say the definition of clustering, is part of the difficulties, because that's where you have to say that I want to emphasize the compactness of the data. So it should be really a rugby team, like all together and give us the ball and we'll move forward. Or whether it's more something like that, so that there should be some space, some separation between the two groups, like those two countries separated by a river or some high mountain. So it's there is no definite, there is no clear notion of what you actually mean by clustering. By which, you can rephrase that by saying that the choice of the metric that you use to train clustering algorithm or to quantify clustering really will have an impact on the results. Voilà. And maybe also a difficulty is that in high dimension, all points are far apart. So if you take really points in really high dimension, no one will be similar to no one. It's just a fact of life. And so that's where, in particular, some preliminary dimension reduction may come in handy. Alors, so maybe the first, there is I have got a whole chapter in clustering methods. Maybe I'll present only the most relevant methods. The one people usually start with is k-means. And this one tries to, so you fix the number of k clusters to find. So you will want to find a partition of your data set into capital K clusters from C1 to CK, and you want them to solve the following problem. So you want to minimize the sum of square errors. So you're going to go over all clusters, and for each cluster, you're going to enumerate the points and to look at their distance to some fixed point. And so, in fact, in the end, it's measuring the distance to the average of a cluster. So that's a computation we have been doing together a few times now, is that when you minimize this over M1 to MK, in fact, it's minimized when for each of the clusters, you replace MK by the empirical average. Yeah, so that's the loss function in k-means. You're trying to separate the data to have this minimal sum of square errors. Check, check, check. And so here it's difficult to, a priori it's a combinatorial problem, which is extremely difficult. Finding the optimal partition, it's a nightmare. Even if you think about two classes, the number of partition of a set of endpoints in two classes is really huge. So you do not enumerate them, and so the idea is to to do something approximate and but randomized. Quoi. And so the precise algorithm is to start from some iterative procedure. We're going to start from some initial partition, which I'll explain how it's done. And then you iterate for t larger than 1 or 0. T larger than 0. By the way, who is familiar with the k-means? Well, okay. Some of you. Here, I don't pretend to have an original presentation. So first, I mean, you update the compute x bar kt, the center of a cluster, the center of cluster ck t, and then you assign the points to the closest cluster center. Closest cluster center. I mean, it's in the lecture notes, it's written in a bit more mathematical terms, but that's really the idea. So you start from some clusters, you compute the, maybe let's do an example. So for typically, you would take points at random. So those round points will be the cluster centers. So you start by sampling those points at random. And after that, and so crosses are my data points. Huh? So you have those random cluster centers, and then you say that, okay, for each of them, I'm looking at which points are closest to one center rather than all the others. And to do that, you do some Voronoi tessellation. You're familiar with Voronoi tessellation? So it's here between 2 points, you're going to draw the line and to draw like the line that goes in the middle, that separates between points which are closer to this one rather than that one. And then you do that for all couple of points, something like that. And in the end, you have constructed something where, comme ça, you have constructed a separation of the space into 4 regions. And in each of the regions, in this region, you're closer to that point rather than to all the others, and so on and so forth. So you have those points, then you have this Voronoi tessellation, and that's your update for the first cluster, second cluster, third, and fourth. Then you recompute the average of the points. So those are the orange points, something like that. Something like that. And then you redo a new Voronoi tessellation. And so on and so forth. And so you keep on updating the partition by this new Voronoi tessellation, then recomputing the centers, and so on and so forth. And in a finite number of steps, it converges to something. Yeah. It could technically, I mean, there is a result about this quantity not increasing. Technically, it could cycle between 2 configurations, but they would have the same error. In practice, it's really, I've never seen it. I mean, in the lecture notes, I give a website where you can really play. I mean, if you're teaching k-means, I mean, this is really great. There is some kind of a movie. You can do step by step that thing with colors and so on. It's really nice. And I've never seen it not converging on that example. But in principle, it could. And so in practice, what is done is that in scikit-learn, for instance, you do some random initialization, and you do like 10 runs, something like that, from 10 random initializations, and you retain at the end the configuration that led to the smallest error over here. So yeah, in any case, that's k-means. One thing that's inconvenient with k-means is that you have to specify the number of clusters. And that, if you do molecular simulation and you don't know whether you've discovered new configuration and how many new conformations you have, well, you just do not have a clue about the clusters there, the number of clusters. So typically, it's it's better if you do not have to specify that, and if you have methods that somehow automatically tell you how many clusters you have. So for that, there is something which is called hierarchical clustering. And there are two versions of it, one which is aggregative, the other one which is agglomerative versus divisive. And typically, it's more like the agglomerative thing that we care about, meaning that we start with each data point is alone at the beginning. It's its own cluster. And then we will merge two of them, two orders of them, and then here like that, and so on. So, I mean, you will find graphs like that for agglomerative clustering, and graphs which tell you that, okay, if I'm cutting at some level, I can identify 3 clusters. And if I cut above, I have 2, and so on. So you can look in diagrams like that. Those are called dendrograms. You have plots, sometimes you have gaps, and then you have clear ways of saying that, okay, maybe I'm cutting at this level or other levels. So how does it work in practice? So I mean, it's an iterative procedure. So you start from all clusters initially as being just xi, and you iterate on t from 0 to n minus 2. So in the end, you will have one cluster remaining is just everyone together. So you start from everyone alone, you end up with everyone together. And the idea, the more interesting thing is the path. So who are you starting to group with, and who are you grouping latest, and so on. And so for that, you're looking for a pair KL which minimizes some distance between two clusters. So at step T, you will have a certain number of clusters which will be n minus t. So first step, so t equals 0, you have t equals 0. Attends, je me suis trompé dans les indices. Ah no, sorry, so smaller than n minus t. So t equals 0, you allow for all values of a of b. And then you've merged one cluster, you have one cluster left, so n minus 1 clusters left. And so at the next step, you're trying to merge two clusters among the n minus 1 that you have left, and so on and so forth. So I mean, here there is a distance, a notion of distance between clusters, which is the key parameter. That this is to be made precise. So first you find that thing, and then you merge CAT, CBT, and keep the other clusters. So that's the partition at step T plus 1 is you've merged two of them and you've kept the others. And so this agglomerative thing, at each step, you're merging two clusters until there is only one left. And in fact, here, I mean, on this plot here, this height would be, if that's 1, 2, 3, 4, 5, the height here would be the distance between 1 and 2. This would be the distance between 3 and 4. Over here, it would be the distance between 1, 2, and 3, 4, etc. So I mean, this, well, I mean, that's the way it's those graphs are being constructed. If I remember well, I mean, in the lecture notes, I'm making a bit more precise how the dendrogram is constructed. But if I remember well, it's that. It's an old version of the lecture notes I have here. So, I mean, the important thing is which distance are we considering here? And that's where you can end up with really various results. And so let me comment a few ones. So something which is called a single link. And then the distance between two clusters, CK, CL, would be the minimal distance xi, xj. So for xi in CK and xj in CL. So that's the minimal distance between two elements. So typically this will favor chaining. So it's this idea, those very elongated cluster where the neighbor looks like the neighbors until you have a really long chain and the first doesn't really look like the last one. That's because you really say that, okay, if you want the minimal distance, you're just looking for adding some element close to one of the elements in the cluster. So I mean here, typically, possibly chaining issue. Complete link. But again, I mean, it depends on what you call a cluster. If you say a cluster is that the new person in a cluster should look like one of the persons in the cluster and that's it, then it's single link. If you say that complete link, you want, it's the same with a max. So somehow you want everyone to be to look close together in the cluster. And there the issue is that you emphasize a compact cluster, so you can have closedness losses because you want compact clusters. So for instance, if you have two sets of data, something that would look like that. So here you have crosses, here you have round thing, and with complete link, maybe single link, you will identify that there are two clusters, but if you do a complete link, then typically you will more have something like that and something like that. So you will lose this kind of closeness within the cluster. And so there's something which is called average link, which tries to balance the two issues. And here it will be like average distance between every two elements in the cluster. So x in CK, xi in CK, xj in CL of the xi, xj. One thing is that this one will be sensitive to monotonic transforms of D. First one, somehow, with its D squares, any kind of increasing function of D doesn't change anything here. If you change the metric, somehow it will have an impact on the clusters that you get. And the last one is something that is called the Ward distance, which is the increase in sum of squares when merging. So you compute the difference between the sum of squares of the points grouped together. Sum of squares being the sum of x minus the mean of the cluster. Kind of variance with the within some form of within variance, within cluster variance, except that you multiply by the number of degrees of freedom. And you measure how much this increases when you merge two clusters. And that's the Ward distance. Voilà. So I mean, that's various choices. And so I'd say that here, in practice, I would say that typically you would choose different distances, compute those dendrograms, and hope for the best in terms of maybe they give clusters which are similar when you cut. And if this is the case, then great news. And if not, then you have to think about which one you want to keep. I'm skipping something which was Gaussian mixture clustering, which is somehow a soft version of k-means, but it's essentially close to k-means. Yeah.
When do you stop your address? Because if you
At the last step, I mean, everyone is in the same cluster.
So you achieve nothing.
So the path is the important thing. It's the way you start by putting things together. So and typically you said, okay, I want to cut at this level. If I want 3 clusters, then you know that those should be the 3 ones. So it's really in the hierarchical structure that the interest of the algorithm lies. Yeah, beginning and end of the story are well known. I mean, you're not there for the end of the story. It's like in some Hollywood movie. You know that the person will survive. You just want to know what she will survive to. Another one, which is a density-based clustering. And this one is I mean, it's rather easy to, it's pretty easy to present. The idea is that here we will have points that some points will be somehow core points which are surrounding by a lot of neighbors. And when you have one, then somehow you form the whole cluster of all the points that are attached to it. And then you do that, you identify, then you have various clusters, and you will have outliers. And so a good thing with that method is that it automatically identifies the number of clusters. So you don't have to specify it, because even in somehow agglomerative clustering, I mean, here you have more of a choice. That you are left to decide where you want to cut, how many clusters you have, and you can use the information on the heights and possible gaps to make educated cuts, I would say. Density-based clustering, you don't even have to do that. It will do it automatically for you, and also leave points on the side as outliers, because maybe you have points in your data set which are outliers. They're just not close to anyone, and maybe the right move is not to include them in any cluster. So for that, so the most known algorithm here is something that's called dbScan, which has a cost n log n. Because one thing I should have said is that some clustering algorithm, for instance, a hierarchical one, it's pretty expensive, because at each step you have to check among the clusters which one to merge. So it's like order n cost at each step, and you have about n steps. So this is the cost here is typically n squared, which if you have a lot of data points, is something which is really too large. So maybe here what you want to start with is to do some k-means, to do some rough clustering, and after that do hierarchical clustering to finish off the job. dbScan is a bit better here, and so it relies on something which is called an epsilon neighborhood of a data, which are all the points in your data set which are at a certain distance smaller than epsilon of the current data point. So say some Euclidean distance smaller than epsilon. So that's the first parameter of the method. There is this notion of what's a small distance, what's small enough for you in order to consider that you have a core point, you have a lot of neighbors around you. And then there is another parameter, which is n-mean, which is the minimal number of neighbors to be a core neighbors. To be a core point. So say do you need 10 data points at the distance less than epsilon to be a core point, or is 5 enough? That kind of thing. And then the algorithm is the following: is that you will pick a data point X which has not been visited. You will mark it as visited. And then if X is a core point, so if it's not a core point, you just go to the next one. I mean, this one has been marked, and it's there. It will not be picked up again. But if you have a core point, meaning that the cardinality of n epsilon of X is larger or equal than n-mean, so you have enough neighbors at a distance epsilon, then you find the set C of all data points which are density reachable, of all points which are density reachable. By that, I mean that I'm considering these core points. All the points in the neighborhood are density reachable. And for each of them, I'm checking whether it's a core point as well. And if it's a core point as well, I'm also putting the neighbors of this point in the cluster. And I do that until I hit the edge of the cluster, essentially. And so all those people together, I mean, they form a cluster. And then you mark all those points as visited. And so when you pick a point, I mean, somehow in a genuine cluster, then boom, all the points are being marked as visited, and another cluster, boom, they're all visited. And for outliers, they just mark one after the other. And sometimes you hit points at the boundary of a cluster. And so maybe this one is just marked as visited. But if after that you hit a core point and it's a neighbor of a core point, this point which was visited will then be attached to a cluster.
There is no partition.
Hmm?
There is no partition.
Yes, there is a partition between, I mean, there are clusters and outliers. But once you're in a cluster, I mean, it's you're in a cluster. It's not like no, because if you had an interceptor, I mean, there could be situations where you would have something like that. So, I mean, maybe this point is a core for one, this one is a core for the other. So I'm thinking on whether this point can be in the neighborhood of this one and this one, but not a core point per itself. Yes, I mean, clusters could overlap, but somehow the point that's in between will be attached to one of the clusters. But I mean, they cannot overlap on a core point. That's clear, because otherwise they would be in the same cluster. So they could overlap on non-core points, and so the boundaries of a cluster are not depend a bit on which order you're visiting the points. So that's density based, and so the good thing is it detects the number of clusters and also some outliers. And last method, which I will not present so much, are spectral clustering. I mean, this one takes a bit more time to discuss. Essentially, what you have is that you see your data as a graph where you have points xi, ej, xk, and then you have weights. So you see the points as vertices of the graph and the weights as weights on the edges. And you construct an operator from there. So some discrete Laplace operator. So an operator which is L, which is D minus W. So W is really the matrix of all those pairwise weights. And D is a matrix whose entries are, it's a diagonal matrix whose entries are dii equal the sum of all the weights attached to so wij for j equal 1 to n. That's the sum of the weights on the diagonal. So this L matrix is some form of a discrete Laplacian on the graph associated with the data points. And the idea of spectral clustering is to do some diagonalization of this matrix and extract the main degrees of freedom. I mean, typically to look at the spectrum of the matrix, and hopefully there is a gap in the spectrum, and so you retain the smallest eigenvalues and the associated eigenvectors, and this will correspond to the clusters. The idea being that the eigenvectors will be more or less constant on the various clusters. So, I mean, I don't really have time to present it too precisely, but it's that's really the spirit in the end, a graph, a discrete Laplacian. Yeah. What's the what? Diagonalizing a n by n matrix. I guess you have the answer to that. Expensive. What choice for W, you mean? Typically Gaussian weights, so something like exponential minus xi minus xj divided by 2 sigma squared. So Gaussian currents, there is a notion of bandwidth. And so it's, I mean, it's pretty similar in spirit to kernel methods. I mean, and there are some interpretations of that as a like in this method, how is diffusion maps as really being like a kernel discretization of Laplacian on a manifold. By the way, if you want to know more about this one in the lecture notes, and I'll stop here. So, and thank you for your attention over those days. It was a pleasure lecturing you, and remain at your disposal if you have questions now or a bit later on. Thank you.
Okay, so now you have a exam.
Ah,
Share.